Here's the thing almost everyone believes. AI knows what a cat is because someone told it. A programmer somewhere sat down and typed in the rules. Four legs, fur, pointed ears, meows. A list of cat facts. Feed it a photo, it checks the list, finds a match. Done. That is the story most people carry around. It is completely wrong. What is actually happening is stranger, and honestly a lot more interesting. AI does not learn from rules. It learns the same way you learn to ride a bike, not by reading a manual, by falling over and over until something clicked. The difference is AI does this billions of times in a matter of hours, and we are going to walk through exactly how. To understand where we are, it helps to know where this idea came from. In 1943, two researchers named Warren McCulloch and Walter Pitts published a paper proposing the very first mathematical model of a single neuron, not a real neuron. A math equation designed to behave like one. They wanted to show that something simple could, in theory, compute. That paper sat mostly on a shelf for 15 years. Then, in 1958, a psychologist named Frank Rosenblatt built something he called the perceptron. It was a machine, roughly the size of a filing cabinet, that could learn to recognize simple shapes. Feed it a triangle enough times, it would eventually get good at triangles. What Rosenblatt had created was simple compared to what we have today. His perceptron could only handle patterns it had seen before, and it could not stack layers of learning on top of each other. For 2 decades after that early excitement, AI research went through what historians call an AI winter. The funding dried up. The promises had outrun the results. But the seed was planted. The New York Times called it the embryo of a computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. That was an overstatement. But Rosenblatt had found something real. A machine that learned from examples instead of rules. The key insight was still small at that point. It would take decades before it became the AI we recognize today. But the core idea, learning by adjusting, was already there in 1958. What changed was computing power and data. By the 2010s, cheap graphics processors originally built for video games turned out to be exactly what was needed to run neural network training at scale. And the internet had produced more text, images, and video than anyone knew what to do with. Those two things, abundant compute and abundant data, turned a quiet academic idea into the technology race of the century. Here is the simplest way to understand how a neural network learns. Imagine you are trying to teach a friend to catch a ball. You throw the ball, they miss. You throw again. They miss, but a little less. Again, they miss, but a little less. Again. After a few hundred throws, they are catching it reliably. You did not explain physics. You did not describe the arc. You just threw the ball, and they adjusted. Let us stay with the ball catching example for a moment because it goes deeper than it might seem. When you learned to catch a ball as a kid, you did not understand the physics. You had no idea about gravity, or the coefficient of air resistance, or the parabolic arc. You just caught it. Eventually. Through failure. Your brain adjusted your muscle responses, a tiny bit at a time, until catching was automatic. The neural network is doing exactly that, except instead of muscle memory, it is adjusting numbers. A neural network does the same thing, except instead of a ball, it is a prediction. You show it an image. It makes a guess. The guess is almost certainly wrong at first. Then the system measures exactly how wrong it was. This measurement is called the loss. Think of loss like a score where 0 is perfect and higher is worse. Once it knows how wrong it was, it makes tiny adjustments throughout the network. It nudges things slightly in the direction that would have made the guess a little less wrong. Then you show it another image. Another guess, another measurement, another round of tiny adjustments. Now do that 10 billion times. That is training, not programming, not writing rules. Just guided, repeated failure at massive scale. One thing people often miss when thinking about how AI learns is the role of scale. It is not just that the math is different. It is that doing it a trillion times changes something fundamental. Imagine practicing a skill 5 times. You get a little better. Practice it a million times, and something qualitatively different happens. The skill stops being effortful and starts being automatic. This is not just true for humans. It appears to be true for neural networks too. Researchers call this phenomenon emergent capabilities. A model trained at small scale cannot summarize text. Train it 10 times bigger, still cannot. 100 times bigger, still no. Then, at some point, something flips, and suddenly it can. No one added that ability deliberately. It emerged from scale. This has happened again and again with large language models. Capabilities appeared that the researchers did not specifically train for, which is fascinating and also a little bit mysterious. The technical name for the adjustment process is backpropagation. You do not need to remember that word. But what matters is this: the network is always working backwards from its mistakes. It guessed wrong, it measures how wrong, it adjusts. That cycle, repeated endlessly, is how every modern AI model you have ever used learned to do what it does. Here is a way to make backpropagation feel more concrete. Imagine you are tuning a very complicated equalizer on a stereo system, thousands of sliders. You play a note and it sounds wrong, so you nudge a few sliders, play again. Still wrong, but slightly less so. Nudge again. After enough adjustments, the sound is right. Backpropagation is the math that tells you which sliders to nudge, and by how much, after every single guess. Inside a neural network, there are layers, thousands of them in a serious model, sometimes hundreds of thousands. Each layer contains neurons, and each neuron is connected to neurons in the next layer. Every single one of those connections has a number attached to it. That number is called a weight. Think of a weight as a dial. It controls how much influence one neuron has on the next. Turn the dial up, that connection matters more. Turn it down, that connection barely registers. When a network is first created, all those dials are set to random values. The network knows nothing. It is just noise. Training is the process of adjusting every single dial over and over based on what the network got wrong. Not a human adjusting them. The math adjusts them automatically. By the end of training, a well-trained network has billions of dials all set to values that, together, happen to produce correct answers much more often than not. The number of weights in a large modern AI model is almost impossible to think about directly. GPT-4, the model behind ChatGPT, is estimated by researchers to have hundreds of billions of parameters. Each one is a small number, a single decimal. Together, they add up to something that can write poetry, explain tax law, debug code, translate between dozens of languages, and pass a medical licensing exam. No single number is impressive. The combination, built through training, is. What is interesting and a little unsettling is that after training is done, no one can fully explain what the network learned. You can look at the weights. There are hundreds of billions of them. But you cannot read them the way you would read a rulebook. The knowledge is in the relationships between those numbers, spread across all of them at once. That is why AI researchers talk about a black box, not because they are hiding something, because even they cannot fully see inside. ChatGPT has hundreds of billions of these weights. No one sat down and set them. No engineer looked at each one. They emerged through training. That is the thing that is hard to wrap your head around the first time you really sit with it. The intelligence in these systems is not written. It is grown through failure, measurement, and adjustment. Billions and billions of times. It helps to understand that modern large language models are trained in stages. First, there is pre-training, where the model is exposed to enormous quantities of text and learns to predict the next word over and over. This is where the weights get shaped. Then there is fine-tuning, where humans provide feedback on the model's outputs, helping it learn to give more helpful and accurate answers. And in the most recent systems, there is additional alignment training, where the goal is to make the model follow instructions and behave safely. Each stage adds layers of refinement on top of the original learned patterns. The reason this matters for us as users is that fine-tuning and alignment can shift behavior, but they cannot erase what was baked in during pre-training. If the original training data contained a pattern, that pattern is in the weights somewhere. It can be suppressed, it can be made less likely to surface, but it does not disappear. Think of it like muscle memory. You can practice a new technique over an old one, but under pressure, the old movement can come back. Now, here's the part that should make you pause. Learning from examples only works if the examples are good. If the training data is skewed, the network learns the skew. If certain groups of people are underrepresented, the network will not know them well. If the data contains errors, the network learns those errors. Training data also shapes what a model thinks is normal. If the vast majority of the text used to train a model was written in English by American and British authors, the model will implicitly carry the assumptions and perspectives baked into that writing. Not just language, cultural assumptions. What a family looks like, what a doctor looks like, what success looks like. The model has no way to step outside that perspective and say, wait, this is just one point of view. It just absorbed it. There is also the question of what data was collected with. Training data for large language models comes from the web, from books, from academic papers. But the web is not neutral. It reflects who has internet access, who writes in English, who gets published, whose ideas get discussed. The model does not know any of this. It cannot reflect on where it came from. It just learned from what was there. There is a well-documented case from medical imaging. A model trained to detect skin cancer was evaluated and found to be much better at diagnosing fair skin than dark skin. Not because anyone intended that, but because the training data included far more images of lighter skin tones. The model learned what it saw. It never saw enough of everything else. This is not a bug in the usual sense. You cannot patch it with a software update. It is baked into the weights. The only fix is better training data or a careful audit of what the model does and does not know. This is one of the biggest challenges in AI right now, and we are going to spend all of episode 2 on it, because where AI goes wrong is at least as important to understand as how it works. This is not a criticism of the people who built these systems. Many of them are well aware of the problem and are actively working on it, but it is something worth knowing as a user. When you ask an AI a question, the answer is shaped not just by the facts it was trained on, but by the particular slice of human output it was trained on. That slice has blind spots. Every slice does. So what does all of this mean for something like ChatGPT? When you type a question and it responds, it is not looking anything up. It is not searching a database. It is not reasoning the way you reason. It is doing something more like very sophisticated pattern completion. Let us also be honest about what artificial intelligence is not. It is not conscious. It does not have intentions. It does not know it exists. When ChatGPT says, "I think" or "I believe," that is just a grammatical pattern it learned to produce. There is no thinker behind the response. There is no belief. There is a very sophisticated text completion engine built from the residue of billions of human thoughts. That distinction matters as these tools become more capable and more embedded in daily decisions. It was trained on an enormous amount of text, from the internet, from books, from code, hundreds of billions of words. And through the process we just described, trillions of tiny dial adjustments, it got very good at predicting what word should come next, given the words that came before. When you ask it a question, it is doing that same thing, completing a pattern. The pattern happens to look a lot like an answer. Think about what it means for a tool this powerful to be shaped by training data in ways its creators do not fully control. When you talk to ChatGPT, you are talking to something built from billions of human decisions about what to write, what to publish, what to value. The AI did not choose those inputs, but it reflects them. Understanding that does not make AI less useful. It makes it more honest to use. That framing matters. It explains why ChatGPT can write a convincing essay about something that is completely false. It is not lying. It is pattern completing. The pattern of a confident answer can be indistinguishable from the pattern of a correct one, because both were in the training data. This is important to hold on to as these tools become part of daily life. This brings up a question that researchers argue about seriously. If an AI can do something, does it matter how it does it? If a model can solve a math problem correctly, does it matter that it arrived there through pattern completion rather than symbolic reasoning? For practical purposes, sometimes no. For trust and reliability and safety, often yes. Because a model that pattern completed its way to a correct answer will also pattern complete its way to a wrong one with equal confidence. The image I want to leave you with: AI is a machine that got extremely good at being wrong. It practiced being wrong so many billions of times with such precise measurement of exactly how wrong that eventually it became useful. That is not magic. It is not intelligence in the way we usually mean it. It is something new, and it is worth understanding on its own terms. There is something profound happening in the world right now that is easy to miss if you only see AI as a product. What we have built in the span of about a decade of serious effort is a technology that learned from the full breadth of written human knowledge, not perfectly, not without errors and gaps, but in a way that was genuinely not possible before. The question of what we do with that, how we use it, what we trust it for, and what we do not, is one of the most important questions of the next 20 years. And understanding how it works is the first step to answering it well. For most of human history, if you wanted to access expert knowledge, you needed to know someone: a doctor, a lawyer, a professor, a financial advisor. That access was unevenly distributed. Now, something trained on a it does not solve the problems of access or inequality, and it brings its own risks. But the underlying shift, a democratization of something that used to be gated, is real, and it is only just beginning. The AI systems being built right now will shape schools, hospitals, courts, banks, and newsrooms. The people making those decisions are not all engineers. They are policymakers, executives, teachers, and ordinary users. The more people who understand how this technology actually works, even just the basics we covered today, the better those decisions will be. Next week, we go into what happens when that process breaks down, the biases baked into the data, the confident mistakes, and why an AI can sound certain about something it has never actually understood. That is episode 2, where AI goes wrong. If you have made it this far, you now have a better mental model of AI than most people. You know it does not work from rules. You know it learns by failing at massive scale. You know that weights are the memory of that learning. And you know that what it was fed shapes what it knows. That is the foundation. Episode 2 is where things get uncomfortable. Because understanding how AI goes wrong requires facing some hard truths about the data it was built from. See you next Friday.